Welcome students. Let us continue the problem in this video also. So we are going with the next example problem on point 16. Come on, go through that problem. A water molecule has an electric dipole moment of 6.3 into 10 to the power of minus 30 coulomb meter. A sample which contains 10 to the power of 22 water molecules with all dipole moments aligned parallel to the external electrical field of magnitude 3 into 10 to the power of 5 Newton per coulomb. How much work is required to rotate all the water molecules from theta equal to initial position theta equal to 0 to the final position 90 degree. So first of all, let us consider what are the given datas. So let us write the datas given. The datas given are, see, go through the problem. A water molecule has an electric dipole moment. So the dipole moment P equal to 6.3 into 10 to the power of minus 30 coulomb meter. A sample contains 10 to the power of 22 water molecules. So the N, let us consider the number of water molecules as 10 power 22. Then all the dipole moments are aligned parallel to the external electrical field. So the external electrical field E equal to 3 into 10 to the power of 5 Newton per coulomb. Let us consider the initial position theta I as 0 degree and the final position theta F taken to be 90 degree. So we have to calculate what is the work done in rotating the dipole from 0 to 90. So let us consider like this: work done in rotating the dipole. Work done in rotating the dipole through an angle theta is equal to potential energy stored on the dipole. Potential energy stored on the dipole is represented as epsilon. So here we have to calculate the difference in work. What is the initial work done? What is the final work done? What is the difference in work done in order to rotate it from 0 to 90 degree? So therefore let us write like this. Here we have to calculate the work done delta W, which is equal to change in potential energy, which is equal to, I can write it in words like this: final potential energy, that is the potential energy got at the final position minus the potential energy got at the initial position. So initial potential energy. So how I can write now? Delta epsilon is equal to final potential energy is minus of PE into cos theta F minus of PE cos theta. Theta is considered to be initial. See, simplify to get the answer. So how you can able to get it out? Change in potential energy is the work done, which is equal to minus of PE into cos 90. Minus of minus will become plus PE into cos 0. This cos 90 tends to become 0. Therefore, we can say the work done is equal to change in potential energy is equal to PE. Since cos 0 is equal to 1. Therefore, the work done is equal to change in potential energy equal to What is the dipole moment? It is 6.3 into 10 to the power of minus 30 multiplied it with E, that is 3 into 10 to the power of 5. So we get multiply 3 into 3, 9, 6 into 3, 18. So 18.9, 18.9 multiplied it with 10 to the power of, see here you are getting it as minus 25, and work done represented in terms of joule. See, at the same time, I can write this as in scientific manner 1.89 into 10 to the power of minus 24 joule. This is the work done on a single water molecule. But what it is asked, how much work is required to rotate all the water molecules? So I have to calculate the total work done in order to rotate all the molecules. So I am writing work done to rotate all 10 power 22 water molecules is equal to work done by a single molecule multiplied with the number of molecules. So let us write like this, W total. So when you are considering the total molecules, work done for single molecule is 1.89 into 10 to the power of minus 24 multiplied it with the 10 power 22. So the answer that you can able to get is 1.89 into 10 to the power of minus 2 joule is the total work done that you can able to get. A simple problem. I hope you should have understood this. Now, the next problem, let us move on. Problem number 1.17. This is problem number 1.16, isn't it? Yes, this is problem number 1.16. Let us move on to the next problem. So the next problem is problem number 1.17. What is this problem? Problem number 1.17. See, go through it. Calculate the electrical flux through the rectangle of sides 5 cm and 10 cm kept in a region of uniform electrical field of 100 Newton per Coulomb. The angle of inclination is 60 degree. Suppose this is first concept. The second one, suppose the angle becomes 0, what is the electrical flux? Two concepts, we can represent it with the help of a diagram. Okay, you are having an uniform electrical field. So this uniform electrical field represented by drawing parallel lines. Inside this, you are having an rectangular region. So of length about 10 centimeter and side about 5 centimeters or breadth about 5 centimeter. And when you are considering the angle between the normal drawn and the electrical lines of force, the angle theta is considered to be 60 degree. This is the first case. Then the second case, see, you are having an electrical field, uniform electrical field, and inside this uniform electrical field, the area available is considered to be parallel to that of what? Parallel to that of the electrical field. So electrical field and the electrical field and the plane of the area are parallel. So the normal drawn is like this. If that is the case, what happens to theta? The theta becomes a 0, isn't it? When you are considering the plane is parallel, then the normal drawn, okay, the normal drawn as well as the plane, so you can take like this, the plane is parallel to that of the electrical field. So the normal drawn n vector and the electrical field E vector are parallel to each other. So theta equal to what? Theta equal to 0. Suppose the angle theta becomes 0. Angle theta becomes 0 means, what do you mean by this? Angle theta becomes 0. The plane should be perpendicular to that of the electrical field. Then only normal drawn and the electrical lines of force will be parallel. Are you able to understood? Theta equal to 0 means plane should be perpendicular to electrical field. Then only theta becomes 0, because the normal drawn and the electrical lines of forces will be parallel to each other. Hope you should have understood this. Now write the data that are being given. First of all, you consider the data. See, calculate the electrical flux. So you have to calculate the electrical flux phi or phi E. Rectangle of sides 5 centimeter and 10 centimeter. So let us consider the area, length into breadth. Length is 10 into 10 to the power of minus 2 into breadth is 5 into 10 to the power of minus 2. So I can write 50 into 10 to the power of minus 4 meters square. Then what about the electrical field? Electrical field E is equal to 100 Newton per coulomb, and initially the angle theta is equal to 60 degree. So what is the flux? Electrical flux phi E. See, let us solve it out here. See, we know that electrical flux phi of E is equal to E into A into cos theta. So what is E? It is 100, or I can write 10 to the power of 2. Again 50 into 10 power minus 4 can be written as 5 into 10 to the power of minus 3 into cos 60. Cos 60 is nothing but 1 divided by 2. So I can write phi of E is equal to 5 into 10 to the power of minus 1 multiplied it with 1 by 2. On simplifying, you will be getting the answer as 5 divided by 2, which is equal to 2.5 into 10 to the power of minus 1, which is 0.25 Newton meter square per coulomb. This we are calling it out as electrical flux for the first case. Let us consider this as A. What is the electrical flux for the second case? For the second case, theta equal to 0 degree. If so, again, flux phi of E is equal to E into A into cos theta. What is E? It is 10 to the power of 2. A is 5 into 10 to the power of minus 3 into cos 0. Cos 0 is 1. So 5 into 10 to the power of minus 1 into 1, which is 0.5 Newton meter square per coulomb. So this is problem number 1.17. Still, we have to go with one more problem. So what is the final problem that we have to see in this video? See, when you are considering this final problem, that is problem number 1.8. Okay, just wait for a minute. See, let us go with the final problem 1.18. I will be reading the problem, and with the help of your book, you just see it. Here it is not opening. So what is that problem number 1.18? See, three figures are being given. From the figure, you have to calculate the electrical flux. What is that electrical flux? Let us see. See, what is the problem number that we have to see here? See, one of the diagram, I am writing it here. The problem is like this, problem 1.18. See, you are given with a charge. The charge that was being represented as plus Q at the center. Since the charge plus Q is at the center, the electrical field acting on this surface is taken to be radially outwards. So you are having the diagram drawn like this. You just look at your book for the diagram. The electrical field lines are acting away from that of the charge, and they are representing an area here as A1. Then nearer to this, they are having another sphere, and another sphere they are having a charge here as minus Q. The area represented as A2 here, and another charge is placed here as plus Q, and this charge is passing through like this. Okay, the electrical lines are passing through the sphere also like this. This is one of the diagram, and let us consider this diagram as A, and we are having the next diagram B. What is that next diagram B? A cubical vessel is considered, a cuboid. Okay, so a cuboid is considered. When I am considering this cuboid, inside this cuboid you are having two charges. One is minus 2Q and another one is plus 5Q, and outside you are having minus 10Q. What it is asked? So number one, the question asked is, in figure A, calculate the electric flux through closed areas, through closed areas A1 and A2. So first of all, let us finish this and then go for the next one. What is the question? From figure A, calculate the electrical flux through the closed areas A1 and A2. So we have to calculate phi of A1, electrical flux through the area of A1, and electrical flux through the area A2. Let us consider using the Gauss law. See, according to the Gauss law, if you are considering the flux available is considered to be equal to the amount of charge enclosed, that is Q enclosed, divided by epsilon 0. See, if I am considering flux of A1, that is the first sphere of area A1, is enclosing a charge plus Q alone. So I am writing it as Q divided by epsilon 0. This is the answer. Similarly, if I am considering flux in that area phi 2, the same formula, Q enclosed divided by epsilon 0. So phi of A2 is equal to, what is Q enclosed? You just consider the second sphere. Inside the second sphere, no charge is available. The charges are outside the sphere. While studying the Gauss law, we have stated that any charge outside the Gaussian surface will not contribute any flux. Since no charge is enclosed inside this surface, we can write this as 0 divided by epsilon 0, which is equal to 0. So flux of A2 is equal to what? Flux of A2 is equal to 0. Similarly, you consider the second problem. What is the second subdivision of this? That is figure B. See, in figure B, we have to calculate the flux available. So from figure B on, in figure B again, phi of the electrical flux is equal to, that is a cubical vessel. Again, the charge Q enclosed inside the closed surface divided by epsilon 0 is equal to, inside this you will be having plus phi Q minus 2Q divided by epsilon 0, which is equal to 3Q divided by epsilon 0. So what is the flux available? Inside this, you see in the from the diagram it is very clear. So we can write this as the electrical flux phi of E inside that cubical vessel is 3Q divided by epsilon 0. Hope you should have understood. Clear? So we have studied up to electrical shielding. Up to electrical shielding, the problems that are being available or being dealt in these three videos, in the three previous videos. Go with the problems, try to work out the problems again and again so that it will be very helpful for you to score good marks by solving the compulsory problems as well as in entrance. Hope you should have understood. Thank you.